Great. So light slows down when it enters a material. And it slows down different amounts based on how strongly it enters, how strongly it interacts with that material. What are the consequences of this? Well, light bends towards, oops, I mispronounced it and misspelled it, towards materials where it is slower. And this is called refraction. Oops, gosh. You know what? Let's just undo. Refraction. So think of it kind of like the way I think of it anyway is kind of like a car driving into a slow patch, something that slows it down. So let's extend this interface over here to the side, and let's draw a little car. Let's draw the path of the car going like this. So the path of the car is coming like this, and the car has a finite width. And the fact is that photons have a finite width too. The larger the wavelength, the bigger the effective size of the photon is. So here's our car. I drew it. Oh my gosh, that's a horrible car. Let's redraw it. We're redrawing it. So here's our car. There it is. And here's our wheels, wheel. And it's coming this way. And as it moves this way, in this direction, the first thing that touches this slow material here is the front right wheel, this wheel here. And that's going to suddenly start moving slower, and the outside wheel is going to keep moving fast. And so what's going to end up happening is this car is going to hit this material and it's going to turn. And so what we're going to get is we're going to get a change in angle relative to the normal. So this is theta 1, and this is theta 2, like over here on this right-hand side. And the light and the car really both turn, like I said, I like to think of it as turning towards the material where it is slower. So what's interesting? Okay. So that is the explanation I gave you is sort of a it's a way of understanding why it happens. But if you want to dive deeper into the physics of it, it's actually a really complex thing to talk about because you know, a photon is in theory it doesn't really have volume, right? It's a wave, but it's a particle. And so why would it turn when it actually enters the material? It doesn't make a whole lot of sense. There's something called Fermat's principle, which says that light always takes the shortest, that takes the least amount of time to get to a point. So if we look at this example here, let's say we're going from, let me add some layers to this real quick. Let's say we're going from this point here down to this point here. If we were to draw and go down a straight line, if our light was to take this path, it's actually spending more time. Oops, that's not what we want. It's actually spending more time in the slow path and less time in the fast path. So it's going faster here, it's going slower here, but it's longer distance in the slow period than this path here. So this path represents an optimal path for time. And actually, if we wanted to, we could do the calculus and describe this geometrically take the derivative, set it equal to 0, and we find out that the minimal time is actually this ratio of angles here. The way that looks is you say that the time geometrically, right? T is equal to the square root of x squared plus h1 squared divided by c divided by n1. And remember, this is the speed of light divided by the index of refraction of 1, the top, and then n2 is the bottom. Plus the square root of L minus x plus h2 squared divided by c divided by n2. And what this says is that, by the way, this, let's define some distances here. This is L, all right? This distance here is x, and this is h1, and this is h2. So you can see that we're really just looking at this length is here. So we'll call this A. This is A, that length, divided by the speed of light in that medium. And this length is B, divided by the speed of light in the second medium, N2. And we add those two times together because the distance divided by speed gives us time. So we add those two times together, and that's the total time. And if we take the derivative and set it equal to 0, d dt equals 0 is equal to n1x divided by c square root of x squared plus h1 squared plus negative n2 L minus x divided by c square root of L minus x squared plus h2 squared. If you rearrange, do some trig substitution, you can find out that n1 sine of theta 1, theta 1 is equal to n2 sine of theta 2. And this is called Snell's law, sort of. Turns out it was originally discovered by a Persian called Ibn Snell. I can't pronounce it very well. He supposedly read Ptolemy's optics and was like, there's a lot wrong with this, and corrected it, which was pretty cool. But again, we're pretty Eurocentric in our science here, so we call it Snell's law, because he was the first European to really write it down. People have since developed 3D vector-based methods where you would say N1 S hat 1 crossed into R1 is equal to N2 S hat 2 crossed into R2. Where S hat is the direction, and I believe R1 is the normal for the surface. Yep. So what this allows us to do is develop a ray tracing procedure. Given a position and a direction of a ray, we can find intersection with the next surface. And then find new direction. And then we repeat it over and over again until we've reached our destination, which is usually a camera or something like that. All right, let's do a quick practice of Snell's law. Here we have an interface where we have air with an index refraction of 1.0 and glass with an index refraction of 1.51. Our theta 1 is equal to 20 degrees. Our angle with the normal is 20 degrees. And our theta 2 is unknown. And I want to know what is our theta 2. So we're going to write out Snell's law, N1 sine theta 1 is equal to n2 sine theta 2. And if we rearrange this, we know that n1 is equal to 0, equal to 1, sorry. And we're solving for theta 2, so we take theta 2 is equal to, sine theta 2 is equal to sine theta 1 divided by n2. And then we can take sine inverse of both sides, and we get theta 2 is equal to sine inverse of sine of theta 1 divided by n2. Plug in our stuff, and we get sine inverse of sine of 20 degrees divided by 1.51. And if we plug that into our calculator, get theta 2 is equal to 13.1 degrees. Cool. So we have 20 degrees, we have 13.1 degrees, and theta 2 is smaller than theta 1, which makes sense because what we said is that our rays always turn into the material with the higher index of refraction. And so it's turning slightly in this direction, right? It's coming back towards the center line, towards the surface normal. This gets a bit harder when surfaces are not flat. So let's say we have sapphire with an index of refraction of 1.77. We have a curved surface with a radius of 10 millimeters. And we have a ray traveling parallel to the optical axis. And an optical axis is just a line which passes through the center of the lens. So this line right here is called the optical axis. And it passes through the center of all the lenses. And it's passing parallel there, so we know its angle, and then it hits the lens and it travels in this direction. And we want to know how much did its angle change? What is theta 2? Well, the first thing we have to figure out is we have to draw our surface normal. Here's our surface normal, and here's our theta 1. And there's our surface normal, and there's our theta 2. So actually, we'll call this theta 2 prime and theta 1 prime to distinguish it from theta 2 in our figure. But I drew that on the wrong side. No, I drew that on the right side. Yeah. So yeah, we did this right. Okay, so actually, yeah, let's call it theta 3 just to be a little bit cleaner. So theta 3. Great. So the first thing we need to do is let's just apply Snell's law and see where it gets us. So n1 sine theta 1 is equal to n2 sine theta 2. Again, we know our n1 is equal to 1 because it's air. This is air out here. Our n2 is equal to 1.77. We're not going to plug that in quite yet. So we know that our theta 3 is equal to sine inverse of sine theta 1 divided by n2. Now the question is what is our theta 1? Well, luckily we can draw this line, and it goes it has to curve a little bit. I didn't do a very good job of drawing it. Actually, you know what? Let's just to make sure this looks clean. Let's erase all this and try again. Our surface normal is going to come from our center of our circle and pass to the point of the intersection of the ray. And then we can define our theta 1 and our theta 3. So since we know it passes through the center of the circle, we can use our parallel axis theorem? I can't remember from geometry. Wow, that was a long time ago. I took that in 1996. We know that this angle here is equal to theta 1. So alpha is equal to theta 1. So we can figure out alpha, we're good. Well, we know our we know this length here is 10 millimeters. We know this radius here is 100 millimeters. So we can calculate alpha. And if we do that, alpha is equal to 5.73 degrees, which is equal to, that would be the sine inverse of, so sine is the opposite over hypotenuse, so it would be 10 over 100 millimeters. Yep, that's about right. Okay, so alpha is equal to this, so we can plug, and we know that alpha is equal to theta 1, so we can plug theta 1 into our equation here, and we get that our theta 3 is equal to 3.23 degrees, which is great. Remember, our light rays turn into the higher index of refraction materials. If we start in a low index of refraction material, our theta 2 should always be less, or in this case, our theta 3 should always be less than our theta 1. Great. But that's not what we want. That's just the distance between the normal here and our ray. We actually want the distance between our ray and the horizontal. So the good part about this is that this entire distance here is alpha. I forget the geometric proof or name of that, reason for that, but that is alpha. So our theta 2 is equal to alpha minus theta 3, which is equal to 5.73 degrees minus 3.23 degrees, so it ends up being equal to 2.5 degrees. Yeah, cool. Then we can figure out where it starts at too, because we can figure out this distance here, right? That distance is going to be equal to 99.4 millimeters. We just use Pythagorean theorem. 100 squared minus 10 squared, square rooted. So that means this distance is 0.6 millimeters. So this ray is going to, after it hits the lens, is going to be starting at a point relative to the lens center. Let's call this 0, 0. Relative to the lens center, this ray is going to be starting at 0.6 comma 10.0 millimeters. And it's going to be traveling at an angle of 2.5 degrees relative to the horizontal, which is pretty cool. Great. So we're going to stop there for now. Obviously, this gets very tedious, right? Ray tracing is a pain in the butt. And we'll post a video in the near future of how we can do exactly this problem with the ray tracing program that I'm giving you guys so that you can compare your results, which will be the first deliverable. But we'll start talking next about approximations we can make to do rough modeling of how lenses will behave, particularly thin lenses.